Cool. I think we're recording. So, hi guys, welcome to the Rust meetup for 4th of December, 2018. Today I'll be talking about ECS, a programming paradigm, which is a different model of storing your data and organizing your logic compared to, say, object-oriented programming. So, how this is going to work, there's a number of slides, there's 87, there's a lot, but in between sections, I'll have some breather slides for some questions about that section that we just passed. So if you feel like something's going too fast, we'll slow down as well. Cool. So, but myself, I used to work in automated distributed system management. Now I'm making a Rust game. All right. So what we're going to go through today, we're going to go through the data organization. We'll compare OO and EC, which is entity component. We'll look at how that's applied in a game scenario, some patterns to solve the problems that come up, and we'll look at how we organize logic. And there's a short summary at the end. So OO, I hope everyone's familiar with this. OO stands for Object-Oriented Programming, P. And so in OO, we usually define data types hierarchically. So if you have a struct or a class, your fields are going to be either primitives or richer types. And if they are richer types, they're going to be their own structs, which further have their own fields as well. And so over here, you can see in this example, we've got a person at the top level. The person has two fields, contact detail, date of birth, and each of those have their own fields down the line. So in code that looks something like this, kind of trivial. And if you have multiple people, you might store them in the world like this. So you have a vector of person. So we tend to call this the array of structs. So the vector is coined the array because it's generally backed by an array, and the person is a struct. And so we tend to call this pattern array of structs in preparation for the next pattern, where we are going to change that into a struct of arrays. So a struct of arrays is you take the same world with the list of people, and you break each person into parts, and you keep the same parts together. So for a person who has contact details and date of birth, instead of having one list of XY, XY, XY fields, you're going to have one vector per field in that top level array. Oh, man.
Someone's really eager to comment and hear you talk.
All right. So remember how we had a person with two fields? So one of them was contact details. The second was date of birth. So we're going to have now two vectors. One that's going to store all of the contact details, and the second one is going to store all of the date of birth. So here, we like to call each field a component because that's one part of the person. And to make sure our data is consistent, each person is represented by one index across both vectors. So that way, if we look at it in pictorial form, index, say, 1, if you go to the contact details of index 1 plus the date of birth, index 1, that's enough data to reconstruct the person. So the person class or struct no longer exists. It's an abstract concept. So some people might think, like, why would anyone want to do that? It's like asking the question, why would anyone want to build like relational databases? And that's not a joke, because this is actually the relational model. And we will see how we do joins later. So why would anyone want to do this? So consider a simple calculation. So you're calculating the average age of people in the world. That's the formula, total age divided by number of people. Now, if we had our person struct and it's stored in the world, we don't really need the world wrapper right now, but you may have the vector of person, and the code to calculate that is to iterate over each of the people, sum everyone's age, and divide by the number of people. So in memory, this is the data that we iterate over. So you can see here on the left, the P0, 1, 2, 3, those represent different instances of a person, and the cells on the right represent the data that you fetch for each person. For calculating the average age, we only need the date of birth, because you need your now minus date of birth, and then that gives you your age. Now, if we do this, if we do the same thing with the struct of arrays approach, we are going to remember how we broke the person into bits. We are going to look at the date of birth for each person. We don't really care about the contact details because that's irrelevant in our calculation, and we iterate over those same logic. Now, if you look at the data that we iterate over, it's as you can see, just the date of birth, and the data that we need is just the date of birth, which like, why should I care about this? Because like usually computers are fast enough, right? So this is actually one of the important questions when you consider should you go with OO or EC data layouts, because if you're not in a performance constrained environment, sometimes having the OO layout is actually better for, say, development effort. So if we consider data locality, when you tell your computer, I want to access this element in this array, your computer thinks, maybe I should fetch some more, because if you're accessing array index 0, computer is going to have some optimizations thinking, oh, you're likely going to be accessing the elements next to it. So it's going to fetch a whole chunk of the array into your cache, because cache access is much faster than main array access. It's like maybe 8 cycles compared to 100 cycles. Yeah. So each process is different, so you can look up the specs for that online. So let's look at how that fits in. So the hierarchical model, so OO model, if you've got bigger elements, you're going to fit fewer elements into your cache. Whereas if you've got smaller elements, the struct of arrays approach, you're going to be able to fit more of those into your cache, and therefore you will get more cache hits and fewer cache misses, and that can shave off quite a bit of time. Yeah, you're going to have more than 5 and 10 because, well, this is just representational. All right, so to see the effects of this, I did write a benchmark, and we can open it. We won't actually run it today, but to get the real stats, I had to increase contact detail size. Whoops, maybe you can't see that. But I had to make contact details really big before you could actually have a consistent result. So to get the array of structs actually having enough slowdown to be comparable. And so if you want to look at the code for that, Rust Cargo, which is a Rust build tool, provides a good way of benchmarking your code, and so the code for this is available online. Yeah, I ran this lots of times, so just to make sure that you could see that there is a definite advantage for cache in terms of data locality when you use the struct of arrays approach. But again, this only applies when you have big enough components. Yeah. I think that's a breather. Yeah. Any questions so far? Yeah.
I don't want to sound like a total idiot, but I think I missed the point where you explained what is ECS.
So we are building up to that point. So the question was, what is ECS?
Like, what does just the letters stand for? Because you keep saying the EC approach. You know.
Oh yes, sorry. So ECS stands for Entity Component System.
Okay.
So each of those is so entity just represents your object, even though you don't have a class for it. Component is like a field in your object, and systems logic that's run over each of the components. Cool. We're good? All right.
One quick question.
Yeah.
Are there any other fields of programming outside of potentially games that ECS is commonly used?
So I don't have an authoritative answer on that, but I do know that if you look on Reddit, there are some people who have asked exactly the same question. Yeah, so there's a thread which I skimmed. I cannot remember the answer though.
Okay.
Yep.
It does feel quite plausible that, as you mentioned, relational databases do it that way. I don't know. But,
There's the columnar stores. They definitely store that
Yep.
that way and have those access patterns.
Mm. Cool. Yeah.
Also, you said that you have to bump the size of your collection. For how much have you bumped it?
So we had to bump the size of the collection. For each element, I increased it by I think 400 kilobytes or something. Yeah, it was quite a big bump. Yeah, 15,000 times 4 bytes, right? Or 600 kilobytes. Yeah, six kilobytes, something like that per element. Yeah. Okay. Whoops. I think there we go. Okay. So we're going to look at how we might use ECS in a game. So if we think of, here's a disclaimer. So the examples here are based on the specs crate, which is an implementation of ECS in Rust. There are other implementations, like Unity has its own, I believe. Yeah. Cool. So in a game scenario, perhaps you have these 4 types. A player is renderable, and you can draw the player. It's got a position in the game, and it can move around, velocity, and it takes input, which is perhaps user controlled. Monster is similar, it doesn't take controls. Speech bubble, you can draw it on screen, but perhaps you can only press next, so it doesn't need to have a position. And the map is special, it's got something called bounds, perhaps to prevent your characters and monsters from walking off screen. Okay, so in the object-oriented model, generally you want to compare good object-oriented design with ECS, or good ECS design. You don't want to compare, say, object-oriented programming syntax with ECS, because people tend to compare, like, this OO design is bad, let's compare it to a good ECS design. That's not really comparing two good things with each other. And also, these bullet points, even though I say these two are under the good design, you can have bad code with interface inheritance and composition as well. But generally speaking, these two are better patterns to use. Alright. So in the object-oriented model, you tend to have, or you could create these interfaces. So the yellow boxes on top here represent the interfaces that each type will implement, and the bottom blue boxes represent each type. So if we look at how this might look like in code, this is a trivial example. So in Rust, you have traits for your interfaces, and you've got your structs, and you implement the trait for each type. And if you want to keep track of your different types in the world, you will have a list of the struct inside your world struct. So the problems that you can get when you are using the object-oriented model, if you think of having some renderable interface to share common logic, it's like common renderable logic for different types, you need to wire those different types through as renderables to the thing that renders stuff. So that wiring code is, you have to write it for each type that you implement. So even though when you implement a trait like renderable for a certain type, you have to do that for whether or not you're using object-oriented style or ECS style. But even after you've done that, in the OO style, you need to also wire that through to the logic that will consume it. In the EC style, you don't have to. We'll see that later. And other problems, well, more like work, I guess you can say. For borrowing parts of an object to process things in parallel, it's much harder in an object-oriented style, because if you want to use the same data across different systems, or different logic, you need to either have immutable references which you share across each of those update functions, or you would have to say copy and clone each of the fields so that they don't end up with having borrow errors. You can look at, so view struct is one of the interesting ones. I only came across like about a month ago. It's pretty much having a layered struct on top of your normal struct, and just having immutable references to the underlying fields, and that way it's easier to pass around. We can look at that in perhaps after the talk. Okay, so in the entity component model, we know that some components apply to some entities. So player, the type, every instance of the player type will have renderable position, velocity, and input. But if we are going to store each of these components in a common vector, we know that across different types, you're not going to have all of those components, which means your vectors, to make sure your vertical slice is still consistent for an object, you need to have empty spots inside those vectors. Cool. And the way we can do that is we can have vectors with option of the component type. Right? We'll get to how we solve these problems, but just as a first step, we break our types into their component fields, and we store each of those components in the same vector. Cool. So and to know which index is a player, which index is a monster, you can keep track of those indices in separate locations. Okay, so the problem that you can see is probably more like problems you can see, right? So there's a lot of empty spots inside those vectors, and so that's usually you get memory bloat, and so other problems you can also hit are entity creation. So every time you want to create an entity, you need to know where to put it inside all of those vectors, and so you can keep track of, say, a U64, but if you always increment, you will eventually run out. And deletion as well. So if you want to delete an entity somewhere earlier in the vectors, shifting everything back is not a good idea, because one, you need mutable access for all of those component vectors, and then you're going to shift all of the memory back. That's not great. Right, so you can see that this is quite problematic. And also, if someone's referencing a particular entity, say an index, they're just holding onto an index for some reason. Perhaps they have a parentable like set of entities, a monster with a weapon. You don't know whether someone's holding onto that, so deleting maybe the weapon and then the monster's still alive, maybe that's going to cause problems as well. So do we have any questions before we look at how we solve these? Yeah.
What's the runtime impact of using? You talk about using interfaces across for things like renderable and that sort of thing. So are you accessing then the underlying objects through as trait objects or something like that? Like, is there a runtime cost to that? Or?
Yeah, so we are accessing them through through a pointer, fat pointer. Yeah. But in terms of components, the entity component style, you don't have to, because the components are stored in its own vector, or storage. It's not necessarily a vector, but because they are concrete types, you don't have that overhead. Cool. Okay. So, generational arena. So some of you think arena, the Colosseum, but it's not like that. So generational arena, it's a pattern in computer science where the arena is a chunk of memory that you request from the computer, and you manage it yourself. So instead of requesting bits of memory, I need this memory for now, and after you've used it, the computer frees it. What you do is you request a huge chunk of memory, and you hold on to the whole thing. And what you can use and use and unused bits of that memory without actually freeing it. And so this way you can save some memory allocation time. And the generational part of this is we use something called a generational index to track where we've got free space inside that chunk of memory. So in this example, we are looking at the generational arena crate. I think Specs has something similar, if not exactly the same. But if we look at what a generational index is, so if you index a vector, normally you just have 0 to n minus 1 as your index, that's your U size. In a generational arena, you've got a second part to it called degeneration. And the generation is something which we use to indicate when was this item put into that memory space. And when we retrieve it, we must point to not just the index, so the position in the chunk of memory, but also the generation that we expect the item to be. So that way we can, if we reuse a slot and we increment, if we reuse a slot, we're going to insert a different item and we're going to use a different generation. So if anyone accessed the same slot with an older generation, we're going to say, no, there's nothing here. We'll see that in pictorial form as well. So the key concepts for a generational arena: you keep a pool of memory. In this example, we have a vector, and we remember which slots are empty. So what we're going to do is we're actually going to fill up the entire vector with an enum, and the enum has two variants, free or occupied. And the occupied variant will contain data if there is data, and it's also going to hold the generation that the data was inserted with. And the free variant will point to the next free slot. We'll see that as well. And every time you free a slot, you're going to keep track of what generation that that slot contained, and you're going to increment a counter to make sure it's at least one more than the slot that you freed. We will see this in an example. So perhaps we'll skip this slide, I just mentioned it. Okay, so we keep a vector here, and each slot will contain an enum variant, so occupied or free. And if it's occupied, you store the generation of the item that you inserted the item with, which is also another thing we track. And when we free it, we need to increment that generation by 1. And we keep a pointer or a reference to the first free slot in the vector. And that slot is going to point to the next free slot, if there are any, and so on and so forth until we get to the end, which will say there's no more free slots. And when we go to the next slide, we're going to populate all of these slots. So what happened is I just populated these 3 elements, and the free list head is going to point to now the last slot. Now when we delete an element, so everything's inserted with generation 0 because here's generation 0. When we delete an element at, say, index 1, we're going to, we know that index 1 is going to be deleted, so when we delete, we're going to track 1 as the next free slot to insert any new data that comes in. And when we deleted it, we knew that that was free, so we're going to update 1 to be a free slot and point it at 4. And at the same time, the generation that we deleted the element at was 0, so we track the next time we insert an element into any slot, it must be generation 1. So what this does, it means that if we delete any other slot which is occupied, because they are all generation 0, we can safely insert new data into those free slots with generation 1, and when anyone queries with generation 0, it's going to say, no, there's nothing at that spot. Whereas if they did query something which did exist with generation 0, we can return it. But if we insert new data, say at index 1 again, it's going to be inserted with generation 1, such that anyone requesting it with generation 0 will get no data back, because the new data no longer applied to the reference they had before. Okay, this is a mind-blowing concept. I took a while to learn it. So just to make you guys aware of this pattern. So what this does solve, so entity creation. So instead of having an ever-incrementing say index that we insert into all of the vectors, we can have this generational arena which tracks. If I want to insert something at, or if I want to insert new data, it knows that slot 1, which was previously used, can be reused. We'll just insert it with a newer generation. So we never have to really keep growing and incrementing our index. And we only increment our index when there's no more free slots beforehand. And for entity deletion, we don't really solve the problem of someone's holding a reference to something which we delete, but at least we can solve the part where if someone's holding a reference and it's stale, we can track that, because if we did not have this generation there and they requested something at index 1 and there was new data at index 1, we'll return them that new data and they wouldn't know that it's invalid. So at least we can solve that problem. And I think we'll go through one more, which we'll look at how we solve the memory bloat problem. So here, entity component storages. So if we use a vector to back every single component that we store, it can be a waste of memory. So in this example, you can see that for renderables, it's okay because we're using every single slot in the vector. But say for positions and so on and so forth, there are empty spaces. And so if you've only got a few entities which have this component, it's going to have a lot of empty spaces. And say if you have 1,000 entities, you're going to have like 1,000 capacity vector for every single vector, for every single component, and that's quite wasteful. So in specs, there are a variety of different storages. So vex storage, we went through. It makes sense for components where almost every entity has that component. Dense vex storage is a different storage where you have one indirection table. So you're going to have a vector which does still have, if you have 1,000 entities, or entities with IDs 0 to 999, you will still have a lookup table with that many slots. But that lookup table can point to a second table where you've compacted all of the components to only the data that needs to exist. So for example, positions and velocities here, if they are bigger than the usize, which is the vectors indexing type, it's going to compress that down. So if you only have, say, two entities that have these components, you're only going to have, say, a data vector which has those two elements. And the lookup table, which is still sparse, will point to the dense table. The dense vector. Another one is Hashmap storage. So if you've got like 1,000 entities, only one of them has this component. You can have a Hashmap which goes from the entity ID to the component type, and it's going to be as small as the, well, like number of components. So say you've got 1,000 entities, you've got one with a particular component, you're only going to have a Hashmap which is really small. Okay, so this different types of storages, they solve the memory bloat problem, and you can have your own implementations, such as like null storage is something which you can tag an entity with, and it doesn't actually store any data for the entity, but when you request, I think it's like a Boolean storage, and when you request that component for the entity, the storage is just going to return a default implementation of that component. Specs has a documentation site which you can look at to see all of the different types of storages it provides. Okay. Breather. Yeah.
With the dense storage,
Yeah.
aren't we giving up some of the advantages of being able to just scan through large vector and get all the birth dates or whatever?
So with the dense vector storage, are we giving up the...
Because it sounds like some of the components will be stored in the original vector, but then some of them that are larger, you only have an index that points to the dense vector. So now there's 2 vectors that you have to scan in order to calculate something like average age.
Okay, so I hope I can articulate this question correctly and then the answer. So if I understand the question correctly, is that because you've got a lookup table as well as the actual component vector, you have to scan both before you can access the...
Yeah.
So if you do have a lookup table, you're going to, it's fast to look up what components are in the, if you have a lookup table and you have an entity index, it's fast to check if that entity has that component. And if you want all entities that do have that component, you do need to go through every index and find out if they have the, like say the date of birth. And I guess in practice it comes down to, is it worth having this dense vector, like this interaction table? And in some cases it's not worth doing that because the component itself is really small. And so like for example, I do have a few components in a project I'm working on that has enum components, and the enum is just like a few variants, and therefore the size of the enum is probably going to be a U8 because it's like less than 255 variants, and therefore if you use a U size to redirect to a U8, it's actually going to be a bigger thing. U size is like 32 bits, I think, so it's going to be 4 bytes to redirect to 1 byte, which doesn't make sense. Whereas if you've just got the plain type, which is really small, it makes sense to just use the vector as well. Hope I answered. Okay. Yeah.
Also, presumably you could just go through the bottom if you just wanted to do all entities. You could
Correct.
Pop over
Yeah. Though I have not gone to that level before in specs, but I do know they provide. I think it's usually unsafe land in there. Yeah. So yeah, you can try. All right. So any more questions actually? Yeah. You first.
Okay. The example you showed had with the generational arena had a generation at the top. So every new allocation was a new generation, or every new frame is a new generation.
Every new hold on, let's go back to that.
Delete, I think it's a new generation. Is that right?
This guy.
Yeah. So just wondering, is there any particular reason to have the generation there? The generation could potentially just live on that element. Each entry in the vector could have its own generation.
Oh yeah, each element does have its own generation.
But the count is global to that.
The count is global to this so that you don't overflow the generation easily. So say if you always use the first 4 slots, but you never really go over 5 entities,
Yeah.
which is a bit strange. But the generation, actually the generation will increment faster that way, because every time you delete, you're going to increment the generation for a particular, for everything. So if you delete generation 0 from slots 0 to 4, you're going to only have generation 1 next, because all of those originally had generation 0. So you don't need to insert anything with generation 2, because 1 is still valid for all of those slots.
Because you could put a generation on the free as well, and just have each individual one have its own generation. It's only possible. Maybe come back to that. It's just it looks like there's 2 potential implementations. I was wondering if there's a particular reason why one would be favoured over another.
Oh yes, true. Yes, yeah. I just got you. Cool. Yes.
Just wondering about the Hashmap storage.
Yeah.
So is it possible to override the hashing algorithm for that? I know the default one's closed.
I believe so. Well, you can implement your own storages as well. So I'm not sure if the Hashmap storage provides you that interface, but I think it uses FNV, which is one of the faster hashes. Yeah.
Oh, okay.
Yeah.
So it already provides a fast hash.
Yeah. I know that there's some other weirdly named hash, like it's named after some animal, but it's supposedly faster than FNV for smaller maps.
FNV is pretty good as long as it's not the default hash. Then it's
Yeah. Oh yeah, and I know the default is designed to be resistant to like hash like attacks or something.
collisions and stuff.
Yeah. Cool. So I think that's our breather. And any questions? Okay, we shall go on. Hey, we have 20 minutes and we have got about 1/3 left. Okay, so the logic part. So logic is how we deal with our data transformations. So let's say we have a task. We want to update positions for anything with positions and velocities based on the if we have anything with a position and a velocity, we want to update the position based on the velocity. So it's pretty much this position plus equals velocity. Really simple. Write the update function inside the class. Hiding the code means better encapsulation. That's what we heard from every CS course. That's not what they said, right? My lecture is out right in front of me. Yep. So OOPS, object-oriented programming syntax. So even if you use interface inheritance, for example here, position update is our trait. If you duplicate the logic across 2 different types, you're going to be increasing software maintenance costs. Because if you say have 100 types, you're actually doing the same thing in 100 places. So you don't want to do that. What you can do for a better design is you can say anything which is positionable and movable, we want to have a common function which updates the position based on the velocity. And I'm going to open this just to show you something fun. Alright, let's make it big. So make it a bit smaller. All good? Can see? Yeah, so can I drag that? I can drag that. I don't know if you can open it if you close it. Alright, so we've got our player type and our monster type, and they both are positionable and movable. You can see here, positionable, movable. And if you're movable, we borrow your velocity immutably, and we will, if you are positionable, we will borrow your position mutably. Cool. Alright, so if we run this, you will actually get, this update function will go through all of the things which are both positionable and movable. I've lost my game object trait. So here, game objects are positionable and movable. And so when we run this, it's going to go through all of the objects which are both positionable and movable, borrow your velocity, dereference it to get the underlying type, and try to update the position. And you're going to see an error saying you're borrowing the game object immutably, and then you're trying to borrow it mutably again, like immediately the line after. Now, interesting thing is if I grab that and put it down here and run exactly the same code, it's happy, right? Because if you look at the output, the player position 0, velocity 1, monster 10 and -1 increments the position of the player by 1 and decrements the position of the monster. So over here you can see that even in a sequential function, you can already get quite difficult, well, obscure borrowing problems. And the problem that you will hit if you try to parallelize this and then parallelize this across like multiple systems, you're going to have a hard time, say, figuring out how to borrow from each different type and keep them running in parallel without having lots of overhead, like wrapping your fields in mutex and that kind of thing. So this is actually good object-oriented design. You are not duplicating your logic anywhere else, but you do need to wire those types through to the same game object, and then you can get the benefits of no duplication. So if we look at this little summary, so the logic is generally pretty clean. Let's make it big. And again, kind of the same list as before. You have to figure out how to borrow or own your data that you are mutating. And that's quite difficult if you go with the OO design. So, well, one of the things you could do, which is probably not a good idea, is to deconstruct your objects and pass them to your different updating functions and then reconstruct them back later and then figure out the priorities of that, right? So that's also going to be a hairy problem. Okay, so we're going to look at how we do this in the ECS style. So systems are the S in ECS, and we're going to look at pictures. So pictures, given a lock or a door, and the door lock has like 2 buttons, position and velocity. That's what the 2 green things are. Wrong button. So this key, the entity, will turn this lock if it has the right teeth, both the position and velocity teeth. So those are the components. This key with an extra tooth will also open this lock because it's still pressing the right green buttons. But this key will not, as in we are missing a tooth. We don't have velocity. So something with position but no velocity, the system's not going to run on that. And we can also do something else. So if we have a lock with a red button for velocity, it wants to run over all entities with a position but not velocity. So kind of like your where not exists in SQL land. So so that broken key will work here, but the working key will not work, right? So that's a little analogy. So the system is the lock, the key, well, the entities are just your IDs, and then position and velocity, those are your components. So when we look at this in code, let's remember this picture. So players have these 4 components, monsters have 3, and so on and so forth. If we go over our storages and join them, we will get an iterator over the entities. No, we will get an iterator over the components for the entities that have those components. So, for example, if we are joining on renderables and positions, players are renderable. Actually, everything's renderable. So all of these will match for the first bit. But when you look at things with position, only players and monsters have position. So only these two types have both components. And so we will get back an iterator over the first and the renderable component and the position component of the player, as well as the render and position components of the monster. And note here that because we do not have concrete types, if you erase these names, you're just iterating over any type with these two components. And for the negative case, we're going to look for anything with positions and not inputs here. So in this case, we know players and monsters have positions, nothing else. So only these who are candidates. And then players have input, but we don't want that, so we take away the player. So we're only going to get an iterator over the monster. And we do get an empty tuple over here. That's how Specs implemented it. I'm not sure for other crates, haven't tried. Okay, so this is just the comparison. So we had this in the object-oriented style, and we have this in the system style, which they would look very similar, right? So if you have good OO design, usually you'll have it's easy to translate into the EC style. Okay, so breather. Any questions so far?
So
Yeah.
with mini games, you basically want to cycle, you process everything, you display, you process everything, you display rapidly. Does that influence how you would design the data structures as well, knowing that you're repeatedly refreshing over everything?
I believe so. So you do have your dependencies, like some functions must run before the others, and that's what you that's how we'll see actually next. And also what those functions do. I think you would generally design both your data, like how you break your data apart, with the way you want to transform the data or operate over the data. So I think the general advice is to keep your components small, so you get that data locality benefit. Though if you think about it the other way, if you want to know everything about one particular entity, your data is split across all of these different storages, right? So you get a bit of a trade-off there. Cool. Let's go on. So system data. Okay, so we saw the function for updating a position. So this is how we put that into a system. So in Specs, the system is a trait, and then the data that it operates over is called system data, and it looks like this. Over here we just have a tuple, and you can have a proper struct as well, and you indicate whether you're writing to a component storage or reading from it. And this is what Specs will use to determine if you can run multiple systems in parallel. Because if you have one or multiple systems all reading from the same storage, that's fine to run in parallel. But if you've got one writer, then we're going to not run any other system when that system is being run. Okay, so how it looks like as a whole. So we've got your system data up here, and it's just got it's got multiple functions, but this is the only one that you really always have to implement. There's other trait functions which let you set up the system. If you look into the details of that, it lets you initialize some things. And there's also another function which they don't really advertise, but it lets you give a hint to the dispatcher, which is the thing that runs the systems, how long the system might generally take to run. So whether it's average, long, or short. And that way it can handle scheduling a little bit better. Okay, so if we go to the next one, this is the dispatcher, which is the layer above the systems. So each system does one particular data transformation, or maybe it displays to the screen. So the dispatcher is the thing which orders those systems. So it keeps track of what systems depend on which other ones, and how many workers there are, and also when I should execute particular systems. So in picture form, it's something like this. This whole box, this big wider box, is our system graph. Any detached node, or any nodes without an incoming edge, are able to be run at the start or anytime they want. But any nodes with edges, they must run in that order. And if you have any two systems which can run at the same time, you first need to make sure that they are not having any data dependencies like mutable and immutable access at the same time before you run them. So yeah, each node is a system I did not mention. So this system must completely run before you can run the others. And each time you tell the dispatcher to execute, it's going to run all of the systems once. So it's pretty much a task flow graph. Okay, so in terms of games, you want to get all of this, the whole system graph to execute within either 16 or 33 milliseconds, because that's what your 60 FPS or 30 FPS you get. Yeah, and I guess if you think of that caching thing we had earlier, if you can shave off like 1 millisecond, it's going to give you 1/16 of your whole processing time to play with. Okay. Yeah, there's a link down here to see how you set this up. Not exactly this, but a system graph. And the thread pool is the pool of worker threads. We use Rayon, which I think defaults to 1 thread per core on your computer. Cool. So I think that's our summary. Yeah. So this is a very short list. I did not flesh it out, but you can see that normally you should compare good OOD object-oriented design with ECS. So not just object-oriented syntax. So you can get good and bad design with ECS as well. The logical partitioning in OOLAN is by object state. So if you want to know what a player is, you can easily open the player type, and then you can see all of the fields it's got, and hierarchically all the way down. In EC, you can't see that. You have storages, and you need to like look in each storage, and you can actually get invalid state. Like if someone just randomly inserts a component into an index where it's meant to be a player, you don't get that safety. Whereas in OOLAN, you can't do that because it's compilation error. But in terms of the logical partitioning, the behavior of anything in an entity component system, so anything with certain components will always inherit the behavior that those components should have. That's a really strange statement, but I'll try again. So anything with 2 particle components, or any number of particle components which should have certain behavior, will have it, because the system doesn't choose based on type. Yep, so you got a visible concrete model in object-oriented LAN. EC, I give it a tick there because you kind of get that for free, but you can have cache optimized compiled code for object-oriented code if you have a really smart compiler. So for example, if you have a sphere and you're trying to compute the intersection of 2 spheres, and you're storing a list of spheres, instead of, so in code you might type you're going to have a list of spheres which stores it in XYZ, in at least in your mental model, XYZ and radius. but you can have compilers which will change that vector of spheres into vectors of x, 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 and y, 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 and z, z, and radius at the same time. So I think Unity has that kind of thing with their C# compiler. So you can get cache optimized code, like native code, if you have a really good compiler. Rust does auto-vectorize, but I heard from someone that it doesn't do it so well for floats. Barrel checker management, entity component model kind of wins there. So I think that's all I had. Ooh, did we fit in time? Yes, we did. Hey, here's you.
I think you've convinced me to try and write a game in Rust.
Oh. You almost convinced me in Python.
Yeah.
Yeah. Oh, yeah, you first.
I was just going to ask a more general question about your game. How's it going? Like how?
So
writing a game in Rust?
I'm finding it so. I'm running a game in Rust, and so I'm using the Amethyst game engine, which backs into specs, and it's, well, one thing, it was a lot easier to do dependency management in Rust, so just switching from whatever languages I was using to Rust saves me a lot in terms of the fluff around the game, right? So that's a big bonus. It's so using specs or ECS, it's not too difficult. I did have to do a big refactoring of like OO style code to EC style code, and that works really well if you are working alone. As in, I did a lot of find and replace, which like I can change 50 files at once, being fearless because of Rust compiler, and as well as adhering to conventions. Because if you have multiple developers, you cannot guarantee that everyone's gonna adhere to the same conventions, and so using find and replace is not going to be a it's not always a good thing with multiple devs. I guess I do have a talk that I want to do on the game when it's like ready. Oh, more ready, yeah.
So specs also has resources which are like singular types, I guess. Is that just a read-write lock, like a RW lock?
So specs has resources. So first I'll answer the resource part. So resource is pretty much like a global variable thing, and you check that into the world as well. So your systems don't always have to work over components. You can also work over resources, which are just any type that you put into the world. Like maybe you're trying to pass information from one system to another, which is not through a game object. You might want to say, all right, the game's paused in one system. Like maybe the input system will say, hey, I received this key, like P or whatever key you use for pause, and then the other systems will read the pause state and decide to not run, that kind of thing. So is it just a read-write lock? Resources are not read-write locks, but then the wrap around it, the read and write, those generic types, those are I think they've got the lock inside them. Yeah.
I presume Rust doesn't yet compile shaders onto GPU cards, but it feels like that model would quite naturally translate onto running on a GPU.
Okay, so
A vector of symbol types.
I know that there is shader compilation at runtime for Amethyst, like when you start is runtime or compile time? It's one of the two. But I think it's probably compile time actually. When you compile Amethyst, it does compile the shaders, because we do have some of those inside the repo. Yeah.
But are the shaders written in Rust or are they written in
No, they're written in GLSL, yeah.
So you mentioned before using ECS, you were doing like object-oriented.
Yeah.
Were you using anything before you used Rust in the games?
Okay, so it went through a few generations. So there was the Java version, there was the other Java version, there was the C++ version 1, 2, 3. I went through like before I knew object-oriented programming. So I started writing this game in high school actually, which is a long time ago. Then I learned about design patterns. So that's the OO part. I switched to C++ because I could not. So one of the artists could not run the Java version on the computer; it was too slow. Yeah. Then, when I went to C++, dependency management was an issue. It's probably still an issue. So I tried out the Maven nar plugin. Then I tried out B code, which was it's dead now, but then it was superseded by Conan.io, and that's maintained by Artifactory now, I think, JFrog, yeah. So that's a Python tool to kind of make life easier for dependency management in C++. But I switched to Rust because I had too many rewrites in that C++ land, and I did fight sig faults which were hard to fight because you don't know where they are. And like Heisenberg, right? When you compile in debug mode, it doesn't show up. But when you compile in release mode, it does, and it's like, oh. Yeah.
Any other questions? No? Cool. I think pizza's arrived. Has pizza arrived? It has? Fantastic. Alright. So I think we'll do pizza now, and for those of you that are keen to stay and potentially just do a bit of a the Go Meetup had this fishbowl session, but I think we might just have a bit of a discussion about 2018 and what people are looking forward to, and potentially have people share some of their knowledge about what is coming, because I'm sure people know like bits and pieces. I know bits and pieces, but maybe there's something that if someone's like, oh, this is gonna change the way that I write games or something like that. So cool, pizza time. Thank you very much for your talk. It was fantastic.